graphical representation. In this section we are trying to use graphs to explain motion. The first type of graph we discuss here is the position versus time graph. The y-axis is the position represented by x, and the x-axis is time. So in this graph we know that the velocity v is dx over dt. So dx over dt is the slope. So in this graph, slope at a given point represents the velocity at that point. So now let's look at some examples. The first graph has a straight line parallel to the time axis. So that means there is no change in the position. So the object is at rest, it's not moving. In the second graph, there is a continuous increase in the position. It has a constant slope. That means this graph represents a constant velocity. In the third graph, we can see the slope decreases with time. So slope decreases means the velocity decreases. The velocity decreases when there is an acceleration in the negative direction. So we can say there is a negative acceleration or an acceleration in the negative direction. On the other hand, in the last graph we can see the slope is increasing, so it's a positive acceleration. The second type of graphs is velocity versus time graphs. So the y-axis is the velocity and x-axis is the time. In this graph, the slope is the acceleration. dv over dt is the slope, which is the acceleration here. From this graph, we can find the average acceleration between point A and point B using delta v and delta t. Delta v is the change in the velocity in that time interval. Delta t is the time interval. So we can estimate the average acceleration by dividing delta v by delta t. It's basically the slope of the line joining A and B, and that represents the average acceleration. But to find the instantaneous acceleration, that's dv over dt, which is the slope at a given point. So by finding slope at any given point, you can find the instantaneous acceleration. Two examples. In the first example, we see a straight line parallel to the time axis. That means there is no change in the velocity, so it represents a constant velocity. In the second graph, there is a constant increase, so it represents a constant acceleration. Now I'm showing how to use what we learned about the graphs to solve a problem. We have given this velocity versus time graph. In the first part there is a constant acceleration, and the second part there is a constant velocity, and the third part there is a constant deceleration in this motion. The first question is find the acceleration of each part of the motion, and the second part find the total displacement. So we know that the acceleration is the slope, so we can find the slope of each section, and that gives us the acceleration of each part of the motion. So in the first part, the acceleration is dv over dt, and that's 24 minus 0 divided by 8, which is 3 meters per second squared. And in the second part, the slope is 0, so the acceleration is 0. Okay. And in the third section, this is a deceleration, so the slope is 0 minus 24 divided by 20 minus 12, which is 8, so it's a negative 3 meters per second squared. The second question is find the total displacement. What we can do is we can find the displacement of each section, and we can add them together. The second part of the problem is find the total displacement. To find the total displacement, we can find the displacement of each part of the motion. So for the first part, the displacement x1 is equal to the initial velocity plus the final velocity divided by 2 times t, that's 96 meters. And for the second part, the velocity is constant. You can multiply the velocity by the time, and that gives you the displacement in the second part, which is 96 meters. And for the third part, again, initial velocity plus final velocity over 2 times 8, and that's again 96 meters. So the total displacement is x1 plus x2 plus x3, which is 288